I also want to thank Cheryl for organizing this very nice format. And yesterday in the evening, we talked about the fact that we want to, at the end, indeed want to talk about more like non-conventional acquisition methods too. And I would like to talk about non-BOLD layer-dependent fMRI very briefly. And like just to give an overview that there is something beyond BOLD. If you want to hear more about it in more details, there's a YouTube playlist about non-BOLD layer-dependent fMRI from real experts in the field. And there's also a review article here. The reason why we want to do non-BOLD layer-dependent fMRI is neurovascular coupling, right? We want to measure something that's closely related to the neuron activity, but we don't really get that. When the neurons fire, there's a lot of different parallel and nonlinear mechanisms involved, which opens up the like arterial vessel here, for example, after a while. Even later, on the venous side here, you also see some oxygenation changes. And this is all very indirect. And you might already see here that the vein comes from somewhere, right? So it does not only represent the local oxygenation changes of those neurons, but also some neurons far away, which is a problem in quantifiability and also with respect to local specificity. So we know that we care about the tissue activity, but in the brain, this comes along with a whole cascade of a lot of different things. We have vasodilation, oxygen consumption, a whole bunch of fluid dynamics until we get to the susceptibility-induced signal increase at the end. This is what we measure with BOLD. We want that one, so it might make sense to get to one of those parameters very close to the tissue activity, close with respect to quantifiability and with respect to localization. And because, for example, we don't really know if all this fluid dynamic is the same across different brain areas, or if it's the same across age groups, or if it's the same if you drank coffee or not. So we cannot really compare the BOLD signal change across participants. If we have something with a physical meaningful value, we can actually compare it. And because of this indirect measure locally, when you go to higher resolution from 3 to 2 to 1 or 0.7 millimeter, usually you still end up with similar fuzzy blobs because most of these veins are not as nicely laminar aligned as the neurons are, as we all know from Jonathan's talk this morning too. So one non-BOLD approach, that is my favorite approach, that is believed to be more closer aligned to the neural activity is VASO, a blood volume sensitive method. And it's a non-invasive method that's based on a T1 selective inversion recovery sequence, which can be understood more intuitively by looking at this two-compartment model here. So here I'm imagining two different spin compartments or magnetization compartments. The red one refers to blood, the blue one refers to gray matter tissue, and then I start every TR with a global 180-degree inversion pulse that flips around these magnetization vectors, and then they decay with different T1 relaxation rates. Blood has a slower relaxation than tissue. This means that the red arrow here crosses the zero line later, right now. And this is the time when we play out an excitation pulse and acquire our signal. So right during this time, we don't have any red arrow, right? So all that signal that we have is coming from everything but the blood. So when we imagine a voxel like that, at this time point, we only see the extravascular tissue. The blood is black. And then when we have activity increase, all the vessels open up. So we have less of this extravascular signal. We have more black blood. This means that the signal goes down, which is basically the concept of the VASO in simplified terms. There are other non-BOLD layer-dependent fMRI methods such as ASL, which does not really measure the amount of blood volume in your voxel, but more the amount of blood volume delivery to your voxel along the vascular stream here. So for example, when we care about the blood volume that's delivered per the unit of time in this lab, you can apply this inversion pulse down there, and then image later, a few seconds later, how much arrived in the slab of images up there. And you can even leave that inversion out and then get some baseline measures of blood volume, blood flow too. And as always with non-BOLD layer-dependent fMRI, it's noisier than BOLD, as you can see here, but it's independent of these large veins at the superficial layers. Maybe even here at higher resolution of 0.8, you should know that this image was acquired over averaging across 10 sessions. So it's very, very noisy. If you do that and worry about registration and everything, then you might see that the blood flow in blue here does not have the big veins in there. So it's a huge price that we have to pay. Another non-bold layer-dependent fMRI method is calibrated BOLD. And so I think usually we talk about things like signal or activity, which are maybe deliberately very loose terms. And from a physics perspective, the ultimate unit of activity is energy. It always eventually comes down to energy. So Ricoh and Davis, they developed this model of trying to quantify the energy consumption. And by knowing that the BOLD signal eventually depends on the overall energy, oxygen consumption, and the amount of of oxygen delivered to your voxel. We have kind of a vascular and oxygen component in that. And we can try to tease those apart by doing so-called calibrated BOLD, which is a series of experiments. In one condition, you kind of try to only manipulate the vasculature. You can do that with pharmacology, or you can do that by breathing CO2, which does not affect the neurons so much, but affects the vessels a lot. Then in a second experiment, you do a neuroscientific task which affects both the neurons and, as a response, also the vessels. This means that for one experiment, we have vessel dilation without oxygen consumption, and in the other condition, we have vessel dilation with oxygen consumption. So when you contrast those two lines of the matrix, you can kind of tease out the oxygen consumption. And this was done in Leipzig, for example, where we did these two experiments, the neuroscientific tapping and the vascular-only hypercapnia experiment, and then putting them into this model, inverting that, you can get some measure of energy consumption across depth. However, you see you need kind of 4 noisy maps to get one value. So imagine the noise amplification. You have a lot of sources of noise, you have a lot of model assumptions. So that's why I think it never really took off. Then obviously having so many methods, it begs the question, well, which one should I use? Which one is the best? And I want to show you some sequence comparison after I talk about that I hate sequence comparisons. And I think nobody should use them because they're never really fair. And it always depends on the measure, on your ultimate quality measure. It's like asking, is a bike better or an airplane? Well, it depends where you want to go. Every method has its place. And there is no winner ever, even though we are really trying to find a winner. So having that in the back of our head, I want to compare all the different non-bold layer-dependent fMRI methods with this kind of fingerprint approach where each method has a certain sensitivity, layer specificity, invasiveness, availability, efficiency, and quantifiability. And the gradient echo BOLD obviously always rules and shines with the sensitivity. But it kind of sucks at a lot of other ones. For example, the layer specificity or quantifiability. Calibrated BOLD shines on the quantifiability, but kind of sucks on everything else, even in the non-invasiveness, because it's kind of uncomfortable to breathe CO2 and you need to have extra ethics. And it's an extra step that makes it harder. VASO might be some kind of compromise between all of them. ASL is maybe the most locally specific, but the sensitivity is lower than other ones. Always for non-bold layer-dependent fMRI, they're noisier, they're more specific and kind of more quantitative. Then putting this into context also with maybe spin echo and grace that we talked about very briefly and that Natalia will talk in more details. In the early days when I was naive and tried to find the best method, we implemented a lot of different spin echo experiments, like spin echo EPI, T2 prep, diffusion weighted T2 prep, or T1 roll, like a spin locking T2 mechanism, and then in 5 participants, and then also in other participants included grace and the ASL, and you can try to compare this and quantify these methods with respect to their sensitivity and specificity, which kind of gives you, depending on how you define those parameters, this kind of cloud. So depending on where you are most limited in your specific research questions, you might use more sequences on that side or on that side. There is no clear single winner. And maybe also with respect to that, I want to say that neuroscience bridges a lot of different spatial regimes, and there cannot be any winner bridging all of them, right? And we have something like clinical neuroscience, where any method that you're using needs to be cheap, super robust, it needs to work across all people, mostly user independent, which I think none of the layer-dependent fMRI tools really fulfills. And we have cognitive neuroscience, where you can get away with more weird sequences, more compromises. You might get away with partial brain coverage and longer experiments. If you really want to go to biophysical, like brain sciences, you have all kind of other ground truth gold standard methods available. You can put electrodes in the brain. You can do invasive contrast agents. So there, VASO spin echo is useless. We have much better methods. On the other side of the spectrum, we have BOLD, and nothing can be as sensitive as that. And I think every method might have its sweet spot, and it has its justification along that curve somewhere. And obviously, we need to bridge everything to get a consistent picture at the end. And that's all I want to say. Thank you. I leave the recording on.
Yes.